Hello everyone, I am Arpan Shaha and today I'll be giving a lecture on MOSFETs, their operation, their structure and their importance in modern electronics. To start off, let's look at why MOSFETs are so important in today's world. The MOSFET was invented back in 1959 at the famous Bell Labs. Before MOSFETs, electronics were very expensive, heavy and slow. But the invention of MOSFET changed everything. Electronics are now very small, lightweight and cheap all at the same time. uh, Everything you see around you, every device you use, your mobile phone, your laptop, everything has MOSFETs in it. So to look at an example, let's look at Apple's M4 chip, which has uh, almost 28 billion MOSFET transistors built onto a single chip. This is something extraordinary. Now, to understand the MOSFET, let's think of a water tap. What happens when you open the tap? Water starts flowing, right? This is exactly what happens in a MOSFET. We have the source, which is the water tank. We have the drain, which is the sink, and the gate is like the handle controlling the tap. So now let's move on to the structure. The MOSFET is a three-terminal device. So we have the source, we have the drain, and the gate, all built on a P-type substrate. The source and drain are N-wells that are doped into the P-type body. We also have a thin oxide layer that separates the gate from the body. So now how do we operate a MOSFET? We apply, so now you can see that there is no conducting path between the source and the drain, but that is what we want, right? So we apply a positive gate voltage, which attracts electrons from the p-type body to near the surface, to the electrons near the surface. You can see that now there is a conducting path connecting the source and the drain. This is the inversion layer. This happens when the gate voltage applied crosses a certain threshold voltage. So now we can say that our MOSFET is a voltage control device. We have previously seen current control devices like BJTs. Now we are seeing a voltage control device. Uh, Not that we have seen the structure, let's look at what MOSFET actually means. The term MOSFET stands for metal oxide semiconductor field effect transistor. The part metal means that refers to the gate contacts, which are made of metal. The oxide refers to the thin oxide layer that separates the metal and the body. The semiconductor refers to the p-type substrate and where the source and the drain are doped, and the field effect transistor refers to the fact that the current is controlled by the electric field generated by the gate voltage. Now, depending on operation, we can categorize our MOSFET into two types. One is depletion type, which you can see on the left. Here there is a pre-existing channel without any gate voltage. So this means that our device is normally on. So we have to apply gate voltage to to deplete the channel and hence turn the device off. On the right, you can see an enhancement type MOSFET where there is no channel when the gate voltage is zero. So our device is normally off. So we need biasing to form the channel and for to create a conduction path. Now in our today's lecture, we'll be focusing on the operation of an enhancement type MOSFET. To start, we have divided the operation into four different regions. The first region is cutoff. As we have seen earlier that we need a certain gate voltage for the inversion layer to occur and the channel to form. So in the first region, the gate voltage is not high enough. So we see that there is no channel that exists between the uh, source and the drain. In this region, our MOSFET is currently off. But as we keep on increasing the gate voltage, the inversion occurs, and we can see that an n-type channel has formed between the source and the drain. So our device is now on, and the current IDS flows from the drain to the source. Now this region is called linear because with an increase in VDS, the current IDS increases linearly. As we keep increasing the drain voltage, we keeping the gate voltage above a certain threshold, we start increasing the drain voltage. Now the increasing drain voltage uh, causes the thinning of the channel near the drain. As you can see that the channel is now thicker near the source compared to the drain. So now we get a wedge like channel. This is mainly because the drain voltage is so high that it starts attracting electrons from the channel to itself, thus making the channel near the drain thin. So this the point, the drain voltage at which the pinching occurs just near the drain is what we call the saturation drain voltage. So this region acts like a transition point between the linear and the saturation regions. Um, so after that we keep increasing, if we increase the drain voltage above the saturation voltage, the pinch off point now starts shifting towards the left, as you can see on the diagram compared to the previous diagram. So now the channel is incomplete, but we still see that IDS is uh, existing. This is because the electrons electrons can jump through through this gap because of the existing electric field that drives the electrons. So now in this region the current becomes constant because increasing VDS won't increase IDS anymore. So this is the saturation region. So now let's map everything we have learned so far onto a graphical representation. We can see that output characteristics maps the drain current versus the drain to source voltage. In lower regions of VDS, we can see that our MOSFET acts like a resistor where the current increases linearly with voltage. But as we cross a certain threshold voltage, which is the saturation voltage in the drain, we see that the current starts leveling off and now has become constant. This is the saturation region. Um, so here current is becoming constant. Also we have another region called the cutoff region where the gate voltage is not high enough to turn on the channel, so we have uh, zero drain current even if we increase VDS. So now transfer characteristics links the output current with the input voltage. We have two curves, for one for low VDS and one for high VDS. We see that below a certain threshold voltage, that is the gate voltage, the gate is off and so no current flows. But once the gate voltage crosses the threshold voltage, the current starts increasing. We have done two plots where we can see that for high VDS, the uh, drain current is very high because obviously with high VDS, a lot of electrons will start flowing through the channel. To summarize what we have learned so far, we have seen that the MOSFET is a voltage control device which are widely used in digital and analog circuits. The MOSFET operates in four different regions: cutoff, linear, and saturation, which can be controlled using VDS and VGS. Also, the channel formation depends on the gate voltage in relative to the threshold voltage. Based on operation, we have seen two types of MOSFETs: enhancement type, which is normally off, and depletion type, which is normally on. Also, we have seen in output characteristics and transfer characteristics how the drain current varies with VDS and VGS. That will be all for today's lecture. Thank you, everyone.